The factors affecting rate of a reaction: when the temperature is increased, obviously rate of reaction will increase. The minimum energy required for the reactants to form activated complex. From reactant to forming activated complex, it needs some energy. As the temperature increases from T to T plus 10, the fraction of molecules having kinetic energy greater than activation energy increases. Hi everyone, this is Harshita Bhavasar from Vidhyaashram PU College, Temple of Excellence. This is the last session of chemical kinetics. We'll discuss now. In the last session, we have discussed about integrated rate equations of zero order, first order and first order of gas phase rate equations, and significance of first order rate equation, and also rate constant for first order gas phase equations. Okay. In today's session, we will discuss about temperature dependence of the rate of a reaction, Arrhenius equation, activation energy, qualitative increase in reaction rate with temperature, and some of the numericals. This is very important concept. And temperature dependence of the rate of a reaction. The rate of a chemical reaction is significantly affected by change in temperature. We have told in the first session itself the factors affecting rate of a reaction: when the temperature is increased, obviously rate of reaction will increase. Okay, for most of the chemical reaction, the rate increases with increase in temperature. For most of the reaction, whenever temperature will increase, the rise in rate of reaction can be seen. The ratio of the specific rate constant of reaction at two different temperatures differing by 10 degrees Celsius is known as temperature coefficient. The ratio of specific rate constant of a reaction at two different temperatures. At two different temperatures, specific rate constant can be seen by 10 degrees Celsius. That temperature will call it as temperature coefficient. The rate usually becomes double for each 10 degree rise in temperature. For each 10 degree rise in temperature, rate will be doubled. So, temperature coefficient equal to Kt plus T by Kt. This is the temperature coefficient formula. Next, Arrhenius equation. According to Arrhenius rate equation, it is proportional to the E to the power minus Ea by RT. The overall equation will be Ks, that is rate constant, is directly proportional to the e to the power exponential of minus Ea by RT. Whenever proportionality symbol is there, one constant should be present. So, here A is there, that is Arrhenius constant. Then what are the other terms? K equal to rate constant, A is Arrhenius constant or frequency constant, frequency factor, R is gas constant, T is temperature in Kelvin, minus Ea, that is Ea is energy of activation. This is Arrhenius equation overall, and these are the terms involved in the Arrhenius equation, which is very much important. And activation energy. The minimum energy required for the reactants to form activated complex. From reactant to forming activated complex, it needs some energy. That energy will be called it as activation energy. It has to activate the reactant to form activated complex. Then activation energy is equal to threshold energy minus average energy possessed by the reactant molecules. Okay, threshold energy minus average energy possessed by the reactant molecules. Then what is threshold energy? Threshold energy is the minimum amount of energy the reactant molecules must possess to form products upon mutual collision. On the mutual collision of reactant molecules, the reactant molecule should possess and should change for the activated complex. That is called threshold energy. Okay. Here hydrogen plus iodine form hydrogen iodide. This is the intermediate complex. This is reactant molecules and it will form activated complex here. According to the Arrhenius, this reaction can take place only when a molecule of hydrogen and molecule of iodine collide to form unstable intermediate. According to Arrhenius, what they told, whatever the reactant molecules, we are taking the example of hydrogen and iodine. Okay, in that hydrogen and iodine, if that overall, according to Arrhenius, the reactant molecule should collide and it should form an intermediate complex to form activated complex. Here hydrogen and iodine are reactant molecules, it should form unstable intermediate, and later it will form activated complex. It exists for a very short time. This unstable intermediate will exist for a very short time, and then it breaks up to molecules for hydrogen iodide. The energy required to form this intermediate called activated complex, and it is known as activation energy. See here, first two reactant molecules, it needs some activation energy and it will form activated complex. In between that, some intermediate will be, unstable intermediate will form. This is potential energy, this is reaction coordinate. Qualitative increase in reaction rate with temperature. All the molecules in the reacting species do not have same kinetic energy. Kinetic energy means virtual of its motion of the molecules. It doesn't have same kinetic energy, and all the molecule doesn't possess same kinetic energy. Ludwig Boltzmann and James Clerk Maxwell used static to predict the behavior of large number of molecules. These two scientists gave the static or prediction of behavior of large molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecules with a given kinetic energy versus kinetic energy. According to them, the distribution of kinetic energy will be given by fraction of molecules with kinetic energy over kinetic energy. See here, fraction of molecules, this is kinetic energy. Okay, here Ne is number of molecules with kinetic energy and Nt is total number of molecules. Okay, and this is the peak, most probable kinetic energy here. The peak of the curve corresponds to the most probable kinetic energy, that is kinetic energy of maximum fraction of molecules. This point is most probable molecule having kinetic energy. The following figure shows the energy distribution curves at temperature T and T plus such that T plus is greater than T. Other than that, we are showing the various temperature energy distribution T and T plus, but T plus is greater than T. At temperature T, the fraction of molecules possesses kinetic energy greater or equal to the activation energy, and it is capable of making effective collisions. At temperature T, because this T is greater than T plus 10, at that temperature, the fraction of molecules will possess kinetic energy greater than or equal to the activation energy. At that temperature T, the molecules will possess more energy or more kinetic energy, and it is capable of effective collisions. After collisions only it will form complex, right? So it will have that much of energy. As the temperature increases from T to T plus 10, the fraction of molecules having kinetic energy greater than activation energy increases. When temperature has been increasing, the molecules having kinetic energy greater than activation energy will appear. Thus effective collision, and hence the rate of reaction increases. Here effective collision will also increases, rate of reaction will also increases when temperature increases from T to T plus 10. See here, this is fraction of molecules versus kinetic energy. This area is showing the molecules reacting with at time, but this additional molecules reacting with time, and this is the energy of activation. Thus, an increase in temperature increases the number of effective collision, results in the increase in the rate of reaction. As the temperature increases, what will happen? Rate of reaction will increases and effective collision will also increases as the kinetic energy will increase. In the graphical method, we will see now. Arrhenius equation, we know that exponential of minus Ea by RT corresponds to the fraction of molecules that have kinetic energy greater than Ea, greater than activation energy. Taking natural logarithm of both sides of equation, ln k, that is we are integrating both the side, ln k equal to minus Ea by RT plus ln A. Plot of ln k versus 1 by T gives a straight line. See ln k, that is rate constant by reciprocal of time gives the straight line having intercept ln A, slope minus Ea by R. Hence, by measuring the slope of the line, the activation energy Ea can be calculated. Using slope of the line, activation energy can be calculated using graphical method. Next, rate constant method. At temperature T1, ln K1 equal to minus Ea by RT1. if the temperature T2, ln K2 equal to minus EA by RT2 plus ln A. A is a constant for given reaction. K1, K2 are the values of rate constants at temperature T1 and T2 respectively. Subtracting equation 2 from 1, we obtain 2 minus 1 ln K2 minus ln K1, EA by RT 1 minus EA RT2. So after substitution K2 by K1, we will take EA by RT as a common, 1 by T1 minus 1 by T2. Ln 2 we have to convert for log. So log K2 by K1, EA by 2.303 into R, 1 by T1 minus 1 by T2. And after here in this part calculation or simplification, T2 minus T1 divided by, see here cross multiplication, T2 minus T1 divided by T1 into T2. This is the log of K2 by K1 equal to EA by 2.303 into R into T2 minus T1 by T1 into T2 is the major expression of Arrhenius equation in the rate constant method. Next is problem. If the rate constant for a reaction is 1.6 into 10 to the power of minus 5 and 6.36 into 10 to the power of minus 3 per second at 600 Kelvin and 700 Kelvin respectively, calculate the energy of activation for the reaction. They have given rate constants and they have given the constant R. What is R? Gas constant 8.314 joule per kilo per mole. And solution. According to Arrhenius equation, log K10, K2 by K1 equal to EA by 2.303 into R, T2 minus T1 by T1 into T2. Substituting the given values, we have log K10, K2, this one, K1, this one, and EA will be, we have to calculate, and 2.303 is a constant, this R is also constant, and T2 700 Kelvin, T1 600 Kelvin. Okay, and here 2.5993, this after calculation 19.147 into 100 by 600 into 700. And here next step is EA equivalent to 2.5993 into 19.147 into 600 into 700 divided by 2.5993. Okay, this only we have cross multiplied. Answer will be 209.028. Okay, 0.9. The unit is joule per mole. We have to convert it into kilojoule per mole. So what will happen? 209.289 kilojoule per mole. This is the A. Okay. And next, the rate constant of a first order reaction becomes 5 times when the temperature is raised from 350 Kelvin to 400 Kelvin. Calculate the energy of activation for the reaction. Gas constant they have given already. According to Arrhenius equation, log 10 5 into K1 because 5 times greater than rate constant. So here only we have to 5 into K1 by K2 equal to EA by 2.303 into R, T2 minus T1. Already they have substituted. 5 into K1, 6.36 into 10 to the power of minus 3 divided by 1.6 into 10 to the power of minus 5 equivalent to EA by 2.303 into 8.314 into 400 minus 350 because T2 is 400, T1 is 350. After all substitution, we'll get 0.6900 equal to EA by 19.147 into 50 by 350 into 400. We have to calculate EA, so we have to take in a left hand side, other things are right hand side. So in the cross multiplication, 0.6990 into 19.147 into 350 into 400 divided by 50. You will get 37474.5 joules per mole. Before that, K2 equal to 5 K1 because 5 times more. That we should not forget because they have given in problem itself. Next, effect of catalyst. Okay, a catalyst is a substance which alters the rate of a reaction and without changing the permanent composition. Catalyst is a substance which alters the rate of a reaction without itself undergoing any permanent chemical change. Its chemical composition will not change, but it will alter the chemical, or it will alter the rate of a reaction in a chemical reaction. For example, in this reaction it will be in potassium chloride, it will form, the presence of manganese oxide, it will form potassium chloride plus oxygen. Intermediate complex theory. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants, resulting in an intermediate complex. How it will form in an intermediate complex reaction? It will form bonds as a unstable intermediate complex, and later it will lead to stable product. This has transitory existence and decomposes to yield products and the catalyst. Just it will form an intermediate complex as an unstable complex, but later it will form or decomposes to yield products and the catalyst. Catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy between reactants and products, and hence lowering the potential energy barrier. See here reactants, it will form a reactant path with catalyst, and reactant path without catalyst, you can also here also see energy, activation energy with catalyst, energy of activation without catalyst. With catalyst energy will be less, without catalyst energy of activation will be needed more. Okay, that's why they are telling catalyst provides an alternate pathway or reaction mechanism by reducing the activation energy. Here without catalyst, see, more activation energy is needed. But if you use catalyst, time will be used less, also activation energy will be used less without any potential barriers. Some characteristics of a catalyst and catalyzed reactions. A small amount of catalyst can catalyze a large amount of reaction. We doesn't want the equal amount of reactant and equal amount of catalyst. A small amount of substance of catalyst only needed to enhance the rate of reaction for a large amount of reactant. A catalyst does not alter free energy change. It does not alter any free energy change. A catalyst does not alter enthalpy change. It doesn't alter the enthalpy change also. A catalyst can catalyze the spontaneous reactions but does not catalyze the non-spontaneous reaction. A catalyst will only work on spontaneous reaction, only catalyzes the spontaneous but not the non-spontaneous reaction. A catalyst helps in attaining the equilibrium faster, that is, it catalyzes the forward as well as backward reaction to the same extent so that the equilibrium state remains same but it is reached earlier. It can work forward also, it can work backward also, and it will reach the equilibrium what we are expecting than fast. And these are the 5 major characteristics of catalyst. First one, once again I am telling, little bit amount of catalyst only needed, or it is enough to alter the large amount of reaction. It will not catalyze the enthalpy change and it will not catalyze the non-spontaneous reaction, just only catalyze the spontaneous reaction, and it will work forward also, backward reaction also, and it will reach the equilibrium rather than expected speed. Next, collision theory of chemical reactions. According to this theory, the reactant molecules are assumed to be hard spheres and reaction is postulated to occur when molecules collide with each other. Here collision means, you know what is collision? One molecule will collide with another molecule. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency. At given time, how much of number of collisions will happen in a reaction? We'll call it as collision frequency. For a bimolecular elementary reaction A plus B product, rate of a reaction can be expressed as rate equal to ZAB exponential of minus EA by RT. ZAB represents the collision frequency of reactants A and B, and e to the power minus EA by RT represents the fraction of molecules with energies equal to or greater than EA. Comparing with the Arrhenius equation, we can say that A is related to collision frequency. All collisions do not lead to the formation of products. We can see the collision frequency or we can see the collision theory, but all collisions will not form the product. Effective collisions are those collisions which lead to the formation of products. The number of effective collisions is governed by the following two factors. As I told, all the collisions will not form the product, but there are so many effective collisions that will lead to the formation of product. For the formation of product and for the happening of effective collisions, two factors are required. Those two factors are energy barriers and orientation barrier. What is that energy barrier? It is the collisions are effective only when the molecules possess energy greater than or equal to the threshold energy. Whenever the energy is equal to or more than threshold energy, the collisions will be effective. What is orientation barrier? The reactant molecule must collide with favorable orientation in order to facilitate the breaking of old bond and formation of new bond. There should be a favorable condition to form or to break the bonds. Then only the reactant molecule will get collide. For example, formation of methanol from bromoethane depends upon the orientation of reactant molecules as shown in below. See here, bromoethane will reacting with alcohol giving rise to methanol plus bromine. Here also delta plus and delta negative is from it is improper orientation and this is with proper orientation. In the proper orientation, intermediate will form, later it will form product. Whenever improper orientation is there, it will not form intermediate also, it will not form product also. So, we have to have the proper orientation to form a product as well as in between the intermediate. The proper orientation of reactant molecules lead to bond formation, whereas improper orientation makes them simply bounce back and no products are formed. To account for effective collision, another factor P called probability or steric factor is introduced. Rate equal to, here this is probability factor, rate equal to P into ZAB, that is collision frequency, into e to the power EA by RT. Thus in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. So by this collision theory, what we have understood? By the collision theory, if you want to effective collision should happen, then activation energy and proper orientation should be present to form a product or the formation of product with the effective collision. This completes the chemical kinetics chapter and this is the very important chapter, as I told, to understand rate of a reaction and to understand the collision theory as well. So I hope you have completely understood whatever I have taught today. We'll meet in the next session. Thank you.